Hello, everybody. We were going to quickly run through a technical talk, a question and answer procedure, and a meeting of minds. I have gotten a couple of questions that were sent to me, and I'm going to address that, but I also thought I would just run through a couple of installation pointers as I go along. The slideshow that I have here is partly for the questions that were sent to me and for the points I would like to make. Unfortunately, if I do the presentation, it assumes that the screen that I have here is actually, I'm going to remove the screen and make it easier. So that should work. Yes. So what I'd like to do is just run through a couple of systems and settings and some of the interesting things about lithium ferrophosphate batteries in terms of use and the performance. So what I have here in the picture here is a system that I did for a telecoms company. And in the top left-hand corner, you have the rectifier with the 4 lead-acid batteries just beneath it. And then to the right, we then have a Revov lithium battery system that was put into test. And it was quite interesting because all we did was take out the positive and negative lines from the lead-acid batteries and direct them across to the lithium batteries. So we connected the positive onto the positive side of the of battery 1, did all the negative cables around from that battery to the other battery to get in series, and then up into the BMS here. And then the BMS did have a what we call a BMV shunt, which is a Victron measurement shunt, and a BMV was sitting just behind the rack mounting in the corner here. So what I would like to just show here is actually of interest, because the rectifier, which is a DC to DC charger, worked very well with the lithium system. It's similar to an inverter, but obviously the inverter is an AC to DC charger. And this particular system turned out to be about 5 times more powerful than the lead-acid systems in terms of the duration of power delivered. I think we ran for 4 days, and at the maximum they'd been able to run the lead-acid was 10 hours. The BMS that I have there, you can see it there, obviously in startup. So it's got, actually it's not, it's 100% full. So it's obviously charged up and ready. I'm looking at those little green lights there. And one of the questions I did receive was that the cable pack that we deliver with the batteries, the question was, one, how do we install those cable packs? And 2, do we have to use those cable packs? Now, the cable packs do come with these cables here, which are the 25 millimeter cables. They do come with nicely attached lugs and a little label on each of them, which will say B minus and P minus and stuff like that. So it will indicate to you exactly where to put the lug and connect it up. On the BMS, this terminal on the right-hand side, as you're viewing it, that's always marked as B minus, so battery minus. battery negative. So you would obviously connect from the battery 2 negative line across into that terminal. The negative current would then run through the inside of that BMS and come out on the other side, the left-hand terminal, and go on up to the rectifier or the inverter. And then you have a little green plug here, which shows you the well, it's the positive connection cable, which gives you the power, the DC power to the system, and that little thing, that cable has a little brown cable that connects across to the positive terminal on the second battery as well, because you want to have a 48 volt system there. I have noticed one or two clients have attached it to the first battery, and effectively they put in a 24 volt power supply to the BMS. In most cases, I've seen that the BMS carries on unfazed by the difference between 24 and 48 volts. I would prefer you to stick to the 48 volt, because I have had one BMS blowout, and I think it was due to that. The cables here, these are all the 25 mil cables, and then this one is a small one. I think it's like a 5 mil cable, maybe even less, 3. They are spec'd for basically a half-meter run on DC, and they're all the right lengths and everything, but most of my clients actually prefer to go to 30 or even 50 mil cable, 35 or 50 mil. And so I'd actually recommend doing 50 mil pretty much all the way down the line. Here on the left-hand side, you do see that for the lead acid batteries, they were originally using 50 mil here, and it was coming across. So that's basically what we just moved those two lines across and used them. But then for the internal system, we used that. Yesterday, I did have a client say to me, we have so many cables now because we're actually using 50 mils all the time. Can we somehow use these smaller cables in a site? And I said, yeah, of course. The terminals that are on the BMS and on the batteries tend to come with 2 bolts per terminal. So there's no reason why you can't have 2 25 mil cables basically doubling up on all the pathways. And you effectively create a 50 mil cable. So they are doing that. And in particular, the cable between the 2 batteries, joining the 2 batteries, so the negative to positive on the battery 1 to battery 2, you can definitely do that. Yeah, just double up on the cabling. Let's see there. So, yeah, the question was that had some cables that they wanted to use, and I said yes, of course. If you have any cables, there is a diagram picture that I can get to later on in this presentation. Site fuses. Now, a lot of people actually ask me, first of all, what is the rating of the fuses you're supposed to have? And the answer is 125 amp. Now, there are 2 components to this. One is that all DC systems must, from the battery, must have the ability to be cut off from the inverter system and the busbar system. So you must have a switch and a fused switch that will blow at a certain amperage. And the amperage that we are specifying here is 125 amps. The reason being is that the BMS will trip at 160 amps, but you don't want to rely on the BMS because that's effectively a 4,000 or 5,000 Rand fuse, when you can actually put in a 200-300 Rand fuse and get a much better performance. So always have that fuse in it. That also meets DC circuit codes and that sort of stuff. Those codes come from, well, they're actually international. So yeah, you can look it up as well. I can send people some documentation I got from Germany about how to do lithium, well, about safe lithium battery installation codes. It doesn't actually give you any installation instructions. It just gives you the sort of health and safety considerations, and it's about 40 pages long. It's very Germanic. If you do want that thing, I'll just comment on this presentation, on this Zoom chat, and we'll get your name down and we'll send it to you. But predominantly, it's largely useless because it's just Germanic and detailed and says the same things you already know. However, you do have to have a fuse disconnect on the positive line, if not the negative line as well, but definitely the positive line. That's a minimum requirement. And 125 amp is rated for steady state amps. So if impulse amp or a surge or a spike amp of about 160 to 180 amps can still go past a 150 amp fuse. So if you do 125 amp, you are 99% confident that it will blow as soon as you get past 140, 150 amps. I do think that the 125 feels conservative, but it isn't. It is indeed a necessary protection for your systems. A lot of people have been asking me if a trip switch or a DC breaker is best. Absolutely, definitely, it is the best. I'll show you in the next slide what I'm talking about, but the DC breaker is just so much more accurate in terms of the current at which it trips. And for that reason, even though I still remain with the 125 amp trip rating, for consistency, you do know that a DC breaker will trip on a surge and a steady state at a much better approximation to 125 amps. One of the other questions that we have is that thin little brown line of the positive to the BMS. That's a little brown line that connects to from the battery positive to the green plug, positive plug for the BMS. Someone asked if they can put in a little DC switch, and yes, one of my clients actually puts in a remote relay that he can activate using GSM, and he can effectively restart the BMS, turn it on and off from the luxury of his own house. The question then is what is the rating for that relay? And it is a 48 volt, and I think it's a 20 amp. I am going to have to find out more, but I think that's the correct rating for that little thin line. But back to the breaker. Typically, the fuse breaker that everyone uses are these big pull-down switches. There's this blue one here, and on the left, and it is you actually clip in your fuses over there, so you can get a 160 or 150 or 125 amp fuse and put them in there. If you have multiple systems and you want to put in some bigger fuses, which a lot of people do, then this is quite a neat and effective way of knowing that you are going to upgrade the DC system with another set of batteries later on. You can put in a system like this, and then all you do is you swap out those little fuses from a 125 to a 250 when you put in another battery set or another 2 battery sets. Still, I would much prefer a DC switch. Now, you can see the next 2 pictures are DC switches. These are actually switches for motorboats and camper caravans, but they would work just as well. And these ones actually are you can put them in the rain, they're waterproof and so forth. But you do have the more typical switch, which is there. There you go. So the computer seems to be slow with the internet. This is the more typical switch that we install in our systems. I don't have that on my system in here in the lab, and I am going to upgrade to them. But the DC circuit breaker that you see there it would trip by itself, and then the customer or yourself can just go over there and pull it back up. And that's very effective if you have a customer in a remote location and you don't want to drive out there and just plug in another fuse. He can just stand there on the phone with you and clip it back up. And then if it trips again, you've still got protection, and you've still got a valid reason to say, no, that there's some circuitry issue, there's some overload issue, and it needs to be addressed without, with some further action rather than just resetting the breaker. The one on the right, I have seen some guys putting in these things which is a big one, it's a 250, and it's actually for 2 or 3 battery sets. They've been putting that in, which is quite nice. The big disadvantage that I would like to stress for everyone is these bolts where the lugs come in for your DC cables. I would like you not to use that as a point bus bar. So in other words, if you have 2 or 3 battery sets, don't attach each of the cables to these points and double them up on the bolt there, on the connection there. Rather put in a nice copper bus bar, and then put this switch in between the battery and the bus bar. Then you can disconnect each battery separately, and you have full protection, and your DC path is not going to be violated or shorted, or by violated I mean you're not going to get some quicker, shorter path or less resistant path from one battery to the other battery instead of all the way up to the inverter. So you could be, if you do a point bus bar system, you could be sharing load or missing some of the current that the inverter actually otherwise would see. So please don't use these little bolts here at the top and the bottom as your bus bar. Rather put in a solid bus bar. Onto lithium curves and setups. So this curve that you see here is this is the curve from that telecom site that I showed you in the very beginning. And it shows you that from the very beginning, they've got AC power, and then on the 22nd of February, about halfway through the day, we turn off the AC power, and we ran we ran the battery for 4 days. And you can see immediately, this is critical, the immediate response on the voltage side is to have a voltage drop of about 1 volt. That's as soon as the load comes on, you will see that, power equal to voltage times current, and you're now drawing current, therefore your voltage goes down. That is a typical lithium response, or the lithium batteries will have that very quick response. It goes down by about 1 volt and then remains level and just keeps on going for basically, in this case, 4 days. You can see here the current was a nice constant draw. It was a telecoms equipment. There's no variation. And then over here at about 49 volts, the curve starts to steepen off until it drops down below the BMS cutoff, when it did cut off. And then when they charged up, they actually charged this one up within an hour. So with a very quick charge up, it was actually too quick. And they were busy frying all of their lead acid systems. So this test was quite indicative of them. But the part that you want to see is to recognize that this little 1 volt drop that always occurs as you put the load on, and towards the end, how the curve starts to steepen. You actually still have a lot of power in here. In matter of fact, this particular current draw here and the whole test ran for 11.5 kilowatt hours. So they were well over the 10 kilowatt hours, but the current was a very low current. If you have a very low current, this thing would just, I think it was 200 watts were being drawn continuously. And so it was just carrying on and on and on, and the batteries would just keep on delivering power. And that's why you get this nice smooth curvature towards the end, showing you the rapid voltage cutoff as you start going towards it's called the knee, as you start going towards the lower voltages. If you have a variable demand, in other words, this current here at the bottom here is busy jumping up and down, and I'll show you that in a second. The voltage, of course, will also jump down. It doesn't quite go all the way back up to this line each time, because you now use some capacity. But it does mean that what you want to do in an area like this, when it gets to around 50 volts, is you want to start looking at cutting off the demand and either starting to supply with Eskom or supply with the sun on the inverter. So we do give you the settings, and I'll show you that now. This is the same battery, the same test, and this is just the state of charge. The state of charge is coming down uniformly, and there's no great variation. That state of charge line matches the fact that the current draw, the watts that were being asked of the system, was constant, unchanging, and therefore the line is very linear. But it's a very nice line to see for a lithium battery. There's no wavering. Yeah. So the main reason why there is such a long, slow curvature here in this picture is the voltage characteristic of the lithium ferrophosphate. And these curves here, I don't need you to really understand the full picture, but these curves here do show you the power zone in terms of voltage of the cells. So basically, from just above 3.1 volts, so this green line is 3.2 volts, to across to 3.4 volts. That's where 80 to 90% of the power of that lithium battery resides. So there's going to be 16 cells, each of them sitting at 3.4 volts. As soon as you hit the load, it will then drop down here to actually to about 3.36, 3.38 volts, and then sit there for the entire time of the battery discharge, slowly going down past 3.3, 3.2, down to 3.1, and at about 3 volts per cell, the full capacity of the battery is utilized. This little diagram does give you a sense of why traditional battery monitoring systems and DC buses do struggle with lithium batteries because the voltage range is so small for each 10% or decade drop in state of charge. And so basically between there and there is 10%, and the voltage change is hardly anything. My meeting will end in 10 minutes. Let's be quick here. So that should give you understanding. And every time you set up your BMSs and your inverters and everything, you're looking to remain within those realms. In which case, if you have a look at our recommended voltages, you'll see that the float charge at 54,5 is 3.4 volts per cell. And the battery disconnect at about 49.5, that is recommended because of by then you're on the elbow or the knee of the voltage curve for the lithium, and you want to want to turn it off back onto inverter or grid power, so the BMS always stays up. And you've got the boost and absorption charge, anything between 57 and 55.5. I do have clients who get down to even 54.9. And the reason why they do that is so that they do have a voltage gap between the surges that might come from solar or from the grid, and it gives you a little bit, like 2 or 3 volts variation. What's it, a padding or a buffer? Thank you, a buffer, so that you can absorb little spikes from the grid. The recommended charge is anything between 60 and 25 amps. 25 amps is what I recommend to people if they're doing a balance cycle. So if you want to balance your batteries after a couple of months of usage, you can run them or recharge the batteries at 25 amps for a couple of days. What it does is it basically gives more time during the recharge cycle to balance batteries or balance the cells. The balancing only kicks in after 3.3 volts. So there is a bit of a pressure to get up to there first, and then it starts balancing, because these are top-end balancing BMSs. The 60 amps is just a recommended. You can do 80, 90, 100 amps. But I'd like to do something in between the two, between 100 amps and 25 amps, to both get the speed of charge up, and then at the same time get an element of balance at the same time. So you can see there the max charge rate I put 90. You can even do 100. So the recharge time is obviously dependent upon the amount of amps you're putting onto there. I do want people to be considerate of the fact that you do want to have about an hour absorption and an hour of float, so that your BMS and the BMV and the inverter bus, so they're all synchronized and they all get to a recognized state of 100%, and they're all sitting at 54.5 volts. So syncing up all the different monitoring systems that are on the inverter and the BMS is quite important. So every cycle should try and get into that absorption and float state. So I'd like everyone to recognize that and know that you want to spend 3 hours charging and another hour in float and absorption, and by then you're already at 1 o'clock and your sun is starting to go down. So bear that in mind in terms of your amp selection. This is actually the curves for Johannesburg. This is the solar incidence average, and I put it up here quickly because there's perhaps an over-reliance on the beauty of solar. People think that putting up 3 kilowatts of panels is sufficient. It is, for the summer months, which you can see here. This is basically talking about 8 or 9 kilowatt hours per square meter. This is solar, what they call radiance, so you can't actually use it. You know, obviously the efficiency losses and everything through the system. However, it's very indicative to see that your average in summer is somewhere around 7.5 during these months, and then drops down in winter to an average of around 3.25, maybe 3.5. So during winter, in the middle of summer, I mean, in the middle of Johannesburg, you actually have a loss of solar irradiation, which is actually something just to bear in mind. This is also complicated by the fact that in Johannesburg in particular, your summer months tend to be with cloud. So what should be a daily occurrence, like we have a look at the day of the 3rd of November, you can see that in the morning they definitely had decent sunlight, no clouds. And then suddenly at just after noon, they started having clouds and then thunderstorms, and you can see that you went down to 0 at one point, and then the storm passed and they had sun. But this is a typical week, which actually was a sunny week in Johannesburg. And all these curves, which should have been nice and smooth, are actually very jagged. And for the first 3 days, you actually effectively only got about 1 day's worth of sunshine. I think the next day, the 4th, was much better, but then it started getting worse and worse. This is just something for you to know. You end up with a big battery, a Revov battery on the corner, and you think you have enough solar to fill them all up, but you don't because of the sun. Voltage discharge curve, I've got the Victron system here. That's the typical curve. I do want to show a nice, graceful ampage coming down, which you can do with the voltage settings. I can indicate that to you in another slide. I'm afraid I'm running out of time here. But what you want to do is set the bulk percentage to about 91%. I know other people like to need it to 98%. That's Tim Murray. But at that point, the current starts to come down gracefully, and then when it reaches into the absorption state, the current comes down quite dramatically. This is the standard Victron curve, and it produces this sort of curve feature, voltage curve feature, and current in a Victron battery. This particular day was nice and beautiful and sunny, but the next day was the same site. It's all over the place. You do see a nice horse's back of the absorption, and then the float over here. So yes, they had a lot of good solar here, but in the morning they didn't, and it eventually got back up there. But this curve here, I'm showing you, that's actually the more typical curve that you're going to see in a photocharger state as compared to this curve here. Final considerations, please. Ground relay, it either must be on or you must already know what your system is doing. Update of the MPPT firmware. Also of the MPPT settings, you must always make sure that the settings, for example, equalization voltage on a Victron system must be set at anything above the absorption. Just something you know, because you do get errors otherwise. Update the inverter firmware. Redo inverter settings every time if you do the update. Lithium phosphate, the charge efficiency is 99%, so you put that in the various set points. Number 6, doing that graceful top end thing, that was this curve here, the blue curve here, where I say you must start bringing down the current as you get up to 100% state of charge. That's been graceful. Stay off the high voltage scenarios. I've got many good scenarios where the system gets cut off and that sort of stuff. And then Felix, if you have two 5K amps with a single set of batteries, in other words, they can effectively draw more than the BMS can supply because they can draw 90 amps each. Can we increase the output of the BMS to supply more than 1C? I'm afraid you cannot. So you do want to limit your the maximum that your aspirates can draw. In scenarios like that, we do like to recommend that you put in a double. You're doing you have to obey the rule of 1 to 2 to 5 to 4. So one for every kilowatt or every kVA on the inverter, you do 2 kilowatt hours on the batteries,